We'll continue our analysis of scattering with the phase shift method. First, we'll review the partial wave analysis. Then we'll discuss the phase shift approach and then apply phase shift approach to 1 and 3D problems, and finally make the connection between phase shift and partial wave analysis and how they are equivalent. So if you recall, with partial wave analysis, we solve the Schrödinger equation from scattering from a central potential by separating the scatter wave into radial function and spherical harmonics. So we have the full wave function psi of r, theta, and phi is equal to r of r, and the spherical harmonics y, l, m of theta and phi. And then we define a function u of r, which is r times capital R of r. And so the Schrödinger equation for the radial component becomes, in terms of u, the following. E times u is equal to minus h bar squared over 2m d squared u dr squared plus the quantity v of r plus h bar squared over 2m times ll plus 1 over r squared, all times u. We then break up space into 3 domains. We have the radiation zone, where you have a simple spherical wave solution, an intermediate zone, where you only include centrifugal term, which is this one, and you leave out v of r, you assume it's approximately 0, and then the scattering region, where you can't make any approximations and you solve the full potential. So then you connect these 3 regions as follows. The 3 equations we have up here. We now look at the radiation zone. We ignored v of r and the centripetal potential, so these 2 are canceled out. And therefore the solution is a superposition of a plane wave e to the I kz plus a scattering factor f of theta times a spherical wave e to the I kr over r. In the intermediate region, we ignore v of r, but we have to include the centripetal term, and it has to match up. This solution in the intermediate region has to match up with the solution in the radiation zone as r goes to infinity. And the solution there was e to the I kz plus k times the sum over L of I to the L plus 1 times 2L plus 1 times A sub L, partial wave coefficients, the Hankel function sub L of the first kind of Kr, and the associated Legendre polynomials, P sub L of cosine theta. This then can be rewritten by using the Rayleigh formula to expand e to the I kz in terms of partial waves with m equals 0 as the sum from L equals 0 to infinity, I to the lth power times 2L plus 1 times the quantity Bessel function J sub L of Kr plus I k A sub L Hankel function of the first kind sub L of Kr, and then P sub L of cosine theta. And finally, in the scattering region, we have to make sure that the solution matches the intermediate region, but we have to include the full potential and solve the full Schrödinger equation in that region. An alternative way of looking at the scattering process is to calculate a phase shift. And the phase shift is gained by the scattered wave during the interaction with the potential. So as it comes in towards the potential and then goes out scattered, it gains a phase shift. And once we calculate that phase shift, we understand how to calculate a scattering factor. So in general, the phase shift is a function of k, and of course then of the energy, which is h bar squared k squared over 2m, of course. So this is completely equivalent to the calculation of scattering amplitudes, as we can see in the 1D example that we'll do in a couple of minutes. In the 1D example, we write an incoming plane wave and an outgoing plane wave with a scattering factor f. So there's a sum of these 2. When we look at it from a phase shift approach, we write the incoming plane wave and then the outgoing plane wave with a phase shift, e to the 2I delta with a minus sign. And these 2 approaches, as we'll show, are completely equivalent. The beauty of this is it simplifies the mathematics And it describes the physics very well. And it says that the potential can only shift the phase of the scattered wave. That's actually an important physical concept. So first what we'll do is we'll apply the phase shift method to a one-dimensional case, then we'll do a three-dimensional case, and finally we'll show how it's equivalent to partial wave description. So in one dimension, let's assume we have a solid wall at x equals 0. We can write the incident wave as psi sub I of x is equal to a e to the plus I kx for x far away from the potential being non-zero. So in the region where potential is non-zero from minus a to 0. And the reflected wave, again, far away from the non-zero potential, we write that as psi r of x is equal to b times e to the minus I kx. So it's a negative going partial plane wave, again, for x is greater than minus a. Now, if we assume that v is equal to 0 everywhere, so there's a hard wall and nothing else, then the full solution is just the sum of the two, because there's nothing that's going to change the scattered wave except the fact that it's scattered and it's reversed its momentum. If you then require that the wave function is 0 at the origin, then that puts a constraint on b, and that b is equal to minus a. And so we can then write the full solution for a one-dimensional case with no potential, with a 0 potential and a hard wall at the origin, as psi sub 0 of x is a e to the I kx minus e to the minus I kx. This actually is an important point. You get a phase shift of 180 degrees. That minus sign flips the phase of the scattered wave. If you have a non-zero potential, the reflected wave will gain a phase shift by passing through this region of non-zero potential. And then since it passes through it twice, going in and going out, it gains a phase shift of 2 delta, twice that phase shift of going through it once. So if we can calculate that phase shift, then we can calculate what the scattered wave is as it traverses the region from minus a to 0. The solution then becomes psi with the potential of x is a times the quantity e to the I kx, so that's the incident wave, minus e to the minus I kx times e to the 2I delta. So this is the phase shift. You have a 180 degree phase shift from the reflection at the hard wall, and the full solution becomes this. Now in 3 dimensions, we have to go back to the expression that we used called the Rayleigh expression that allowed you to express a plane wave as a sum of partial waves with m equals 0. So the plane wave is just a sum of partial waves. And those partial waves look like this. Sum of from L equals 0 to infinity, a I to the nth power times 2L plus 1 times Bessel function J sub L of Kr times the associated Legendre polynomials P sub L of cosine theta. Each partial wave, that is each value of L, has a different total angular momentum and it scatters independently. So J sub L of x can also be written in terms of Hankel functions because the Hankel functions were sum of Bessel and Neumann functions. So J sub L is 1/2 times the quantity H sub L of the first kind of x plus H sub L of the second kind of x. And when you assume that you're far away from the scattering center, that is, x is much, much greater than 1, or in this case, Kr, that is, r is much, much greater than 1, then you can rewrite these, given a 0 potential everywhere, as 1 over 2x, approximately 1 over 2x, minus 1 to the L plus 1 power, e to the ix, plus I to the L plus 1, e to the minus ix. So that's the expression of the Bessel functions when you're far away from the scattering center. and the potential is 0. So for the Elf partial wave at large values of r, we can write psi 0 of L, which is the Elf partial wave, is A times 2L plus 1 over 2IKR times the quantity e to the IKR minus a minus 1 to the Elf power e to the minus IKR. So what we've done here is we've factored out the minus 1 to the L plus 1, and so you get e to the IKR, which is your incident. It's an incident wave. And here you have a scattered wave going in the negative direction, back out, times the associated Legendre polynomials p sub L of cosine theta. And this is for v of r is equal to 0. So the second term is an incoming spherical wave, right? Because you have an r here, 1 over r, and e to the minus IKR over r is an incoming spherical wave. And the first term is the outgoing wave. So this e to the IKR over r is an outgoing spherical wave, which is phase shifted when there's a non-zero potential. So psi of L is approximately equal to A times 2L plus 1 over 2IKR, e to the IKR, e to the 2I delta sub L, so this is the phase shift for the Elf partial wave, minus a minus 1 to the Elf power e to the minus IKR, times the associated Legendre polynomials p sub L of cosine theta, for v of r is non-zero. Now what we want to do finally is to compare the result that we have for the phase shift method, delta sub L, where these are the phase shifts, and the partial wave expansion, partial wave analysis, where you have partial wave coefficients, A sub L. So for the phase shift method, psi of L, the Elf partial wave, is equal to A times 2L plus 1 over 2IKR times the quantity e to the IKR e to the 2I delta sub L minus a minus 1 to the Elf power e to the minus IKR times p sub L of cosine theta. And the partial wave solution that we had before was the Elf partial wave was A times 2L plus 1 over 2IKR e to the IKR minus 1 to the Elf power e to the IKR, e to the minus IKR, plus 2L plus 1 over r, A sub L, e to the IKR, times p sub L cosine theta. So this is the incident wave as expanded by the Rayleigh expansion, and this is the scattered wave with the scattering factor f of theta, which depends on the partial wave amplitudes. Now, if we keep the terms that do not cancel, you can see this term is identical to this term, and you can get rid of the p sub L cosine theta because it's in place in both cases. So only the terms in red need to be equated to make these two equal. And so you get, from the phase shift analysis, you get 2L plus 1 over 2IKR, e to the 2I delta sub L, e to the IKR. And from the partial wave analysis, you get 2L plus 1 over 2IKR, e to the IKR from this first term, and then 2L plus 1 over r, A sub L, e to the IKR from the second term. You can now drop the e to the IKR. You can cancel the 2L plus 1. You can cancel the 1 over r. And you're left with an equation that you can solve for A sub L. Just bring this over to this side, and you have a term with a phase shift. They're exactly identical. So it's 1 over 2IKR. One has a term with a phase shift. The other one does not. And so you get that A sub L, the partial wave coefficients, are equal to 1 over 2IK times e to the 2I delta sub L minus 1. So you have an equivalence between the partial wave expansion coefficients and the phase shift, individual phase shift for a partial wave. Well, I can do a little simplification by pulling out the e to the I delta sub L from both terms. So I have, and then I bring the 2i underneath what's left. So I have 1 over k e to the I delta sub L times the quantity e to the I delta sub L minus e to the minus I delta sub L over 2i. But this clearly is just a sine function. So this then becomes 1 over k e to the I delta sub L sine of delta sub L. So the partial waves coefficients are directly related to the phase shifts. So the partial, if you look at the partial wave calculation, you can now pull out the scattering factor and the total cross-section in terms of these phase shifts. So f of theta, in terms of the phase shifts, is our 1 over k, sum of L equals 0 to infinity, because you have to sum all the partial waves, times 2 of 2L plus 1 times e to the I delta sub L sine of delta sub L, p sub L of cosine theta, and the total scattering is 4 pi over k squared, sum of L equals 0 to infinity, 2L plus 1 times sine squared of delta sub L.